Today's lesson is on the area of polar curves. So this is going to be different than just regular rectangular area. So if f of theta is continuous and non-negative, and this is a big deal, then the area enclosed so we'll go from A to B. We're going with the angles, and I'll draw a picture here in a minute, of r equals f of theta, and the lines theta equals alpha and theta equals beta is these formulas here. Okay, so it's 1/2 the function squared, or 1/2 r squared. The biggest thing is that it has to be a positive value. So in a lot of these curves, what we're going to end up doing is using the symmetry and the fact that the graphs are symmetric to find the areas. If we have more than one, then we'll be subtracting the two, and it'll be outside minus inside there. I put some useful substitutions here because when we're integrating, a lot of these end up involving a sine squared or a cosine squared. So remember that for those we need to do these substitutions. So since cosine 2 theta equals cosine squared minus sine squared, that means either cosine 2 theta is 1 minus 2 sine squared or 2 cosine minus 1. When we solve for the sine and cosine, we get these two equations. So anytime we're integrating sine squared, we're going to integrate this. If we're integrating cosine, we're going to integrate this. So on the Canvas page, I've included this document, which is just a reminder of what all these different polar curves are. So back in pre-calc, we talked about a rose is going to be a cosine n theta and a sine n theta, and we get a graph like this. Remember that if n is even, then you have 2n number of petals. If n is odd, then you have that many petals. A lemniscate, we won't use these too much, but those look like that. Limason, we'll do a few of these. Cardioids you see quite a bit. So the cardioids are a plus a cosine and a plus a sine. Circles can just be a circle at like a or like 2, so this would be r equals 2. R equals cosine theta and r equals sine theta. A line through the origin would be theta equals a. If you have r cosine theta equals a or r sine theta equals a, this would be a vertical line because that would be x equals a. This would be a horizontal line, which would be y equals a. And you'll see those as r equals cosecant and r equals secant because you divide. The other thing to remember is that if the function has a sine in it and nothing else, then it's symmetric to the y-axis. And if it has a cosine, it's going to be symmetric to the x-axis. And it may be symmetric to more, but for example, these circles, a cosine is going to be symmetric to the x-axis, so it's going to look like this, versus a sine, which is going to look like this because it's symmetric to the y-axis. Okay, so we're going to find the area of the region bound by the graph of r equals sine theta. So we just talked about what that graph looks like. That's going to be a circle symmetric to the y-axis up here with 1. So they already give us the integration bounds. So this is going to be the integral from 0 to pi of 1/2 r squared, which in this case is going to be sine of theta squared. So this is going to be 1/2 times the integral of 0 to pi. Sine squared, when we want to do that integration, we substitute that with 1/2 1 minus cosine 2 theta. Okay, so we'll integrate. I'll go ahead and put that with that. So 1/4. Then on the inside here, the integral of 1 is going to be theta. The integral of a negative cosine 2x is going to be a 1/2 sine 2 theta. We're going to evaluate this from 0 to pi. So this is going to be 1/4 pi minus 1/2 sine 2 pi minus 0 minus 1/2 sine of 0. So that's 0, sine of 2 pi is 0. So all we have left here is pi, so this is going to be pi over 4. So what we did here, the cross sections are actually go from the center. So we have to, you integrate, so this one was 0 to pi because it starts at 0 and ends at pi. But our cross sections go from the radius rather than being a vertical line or a horizontal line. All right, we're going to find the area of a circle is pi r squared, or pi a squared. So if we have a circle, r equals a, it's going to look like that. So we're going to have the integral of 1/2 r squared, which is going to be a squared, d theta. And we're going to go from 0 to 2 pi. So this is going to be 1/2 of a is just a constant. So this is going to be a squared theta from 0 to 2 pi. So we're going to have 1/2 times 2 pi squared. Sorry. We're going to have 1/2 a squared times 2 pi. Forgot, theta's our variable, not a. Minus 1/2 a squared times 0. Well, 1/2 times 2 is 1, so we end up here with pi a squared. All right, so we have f of theta is r equals 1 minus cosine theta. This is a cardioid. Okay, so we're going to graph it rectangularly. So the amplitude is 1. The period is going to be 2 pi, and we have a vertical shift of 1. So we have a negative cosine, so it's going to start at the minimum. All this stuff from pre-calc coming back. All right, so there's my graph. So for what values of x, y is greater than 0 is where y is greater than or equal to 0, meaning non-negative. All of them. So from 0 to 2 pi, the whole graph is positive values, so that's a good thing. So does the formula hold? Yes, because it's all positive values. So we're going to find the area. So the area here is going to be the integral from 0 to 2 pi of 1/2 r squared, which in this case is 1 minus cosine theta squared. Okay, so I'm going to pull the 1/2 out. We'll FOIL this, so we'll have 1 minus 2 cosine theta plus cosine squared theta. Okay, for the integral of cosine squared, we need to do the double angle replacement. Which is 1/2 1 plus cosine 2 theta. So again, on this homework assignment, you're just going to be typing these in the calculator, but eventually you do need to be able to do these by hand. So we're going to have a 1 plus a 1/2 if I distribute this in. So that's going to be 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta. Okay, now we're going to integrate. So this is going to be 1/2 3/2 theta minus 2 cosine sine theta plus 1/2 times 1/2 sine 2 theta, evaluated from 0 to 2 pi. So we're going to have 3/2 times 2 pi. Sine 2 pi is 0. Sine 4 pi is 0. And then if we plug in 0, all that's going to go away. So we have 6 pi over 4, which would be 3 pi over 2. Okay, then we're going to graph the cardioid by hand. And I'm just going to use these points. So at 0, we're at 0. At pi over 2, we're at 1. At pi, we're at 2. At 3 pi over 2, we're at 1. And then 2 pi, we're at 0. So how does that translate to the polar curve? At 0, we're at 0. Pi over 2 is at 1. Pi was at 2, and this was at 1. So the cardioids are the heart-looking ones. And you can graph it on your calculator to confirm. Remember, just go to polar mode and then graph that in. Then we're going to set up an integral to find the area in the first quadrant. Okay, so this is going to be the integral from 0 to pi over 2, that's the first quadrant in polar, of 1/2 r squared. And then we type that in the calculator and get 0.178. Now if you're in polar mode, these will be thetas. If you're in rectangular, it'll be x, but you'll still get the same thing. Now we're going to graph sine 2 theta. This is going to be a rose. And we're going to graph it for 0 to 2 pi. So our period here is now going to be 2 pi over 2, which means our period is pi. So we're going to actually have 2 cycles from 0 to 2 pi. So for this one, it's sine, so it's going to start at the midline, goes through 1 cycle in pi, and 2 cycles in 2 pi. All right, so what values of x make y non-negative? Okay, so where is it positive? Well, that's going to be between 0 and pi over 2, and then again from pi to 3 pi over 2. So will the integral from 0 to 2 pi give us the area? It will not, because you're going to have positive area and negative area, and that's going to cancel each other out. So we're going to graph this rose. I'm going to make myself a little circle at 1. Okay, and the peaks, the petals are going to be where these are at the maxes and mins. So at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, and we can verify using the calculator. So just to remind you, if we go to mode and then go to polar mode, when you go to your y equals, you just graph it like that. For my window here, I know it's going to be pretty small. So we'll go from 0 to 2 pi, and then go from maybe -3 to 3 null. So there's our rows. If you want it to look prettier, you can do a zoom square, and then it looks more symmetric. Okay, so we're going to set up and evaluate an antiderivative that finds the area inside one petal of the curve. Okay, so we're going to find this petal. So we're going to have the integral from 0 to pi over 2, because that's going to be the area for the first petal. 1/2 sine 2 theta squared so we're going to have the integral from 0 to pi. I'm going to put the 1/2 out front. Okay, so I am again going to have to do the double angle substitution for this sine squared. So this is going to be 1/2 1 minus sine 2 theta, which in this case my theta is 2 theta, so this is going to be sine 4 theta. Cosine. Minus cosine 4 theta. Okay, let's integrate. So we have 1/4. The integral of 0 is going to, or the integral of 1 is going to be theta. This is going to be a 1/4 sine 4 theta. And we're doing this from 0 to pi over 2. This is going to be 1/4 pi over 2. If I plug in pi over 2 here, we're going to have 4 times pi over 2, which would be 2 pi. Sine of 2 pi is 0. And then if I plug in 0, we get 0 and 0. So this is just going to be pi over 8. So now how would I find the area of the entire rows? Well, this was one petal, so 4 times that is the area of the entire rows. So find another integral that represents the entire area. So we can't just go from 0 to 2 pi, but what we can do is take one petal and multiply it by 4. So now we're going to do a problem that involves two curves. So we have r equals 4 plus 4 cosine theta, which is a cardioid. And we have r equals 6, which is just a circle at 6. So we're going to graph these. So the circle is just going to be out at 6 units. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Okay, so there's my circle. Then we're going to draw the cardioid. Okay, so if I plug in 0 into this equation, cosine of 0 is 1. So we get 8. Cosine of pi over 2 is 0, so 4 plus 0 is 4. Cosine of pi is negative 1, so this is going to be 0. And then at 3 pi over 2, we'll be at 4 again. Sorry, so we graph our 8, 4, 4. So our cardioid is going to look something like that. Okay, we're going to find the intersections, and we'll do that by setting the equations equal to each other. So 4 plus 4 cosine theta equals 6. 4 cosine theta equals 2, which means cosine theta equals 1/2. That's going to happen at pi over 3 and negative pi over 3. Okay, so we're going to join each intersection to the origin with a line. So from here to this intersection, and from here to this intersection. So this is the theta equals pi over 3. This is the theta equals negative pi over 3. So our first task here is to set up and evaluate an integral for the region that is inside the cardioid but outside of this circle. So that's going to be this area here. So this would be the integral from negative pi over 3 to pi over 3 of 1/2, and it's going to be the outside minus the inside. So the outside is going to be the cardioid, minus the inside, which is 6. And we can just let the calculator do this for us. So you just type it in as you see it, and you get 18.611. The alternative, and something that's really pretty frequently used in these polar graphs, is you can use the symmetry. I could have done 2 times the integral from 0 to pi over 3 to evaluate this, which I will do in the next case. Okay, the next one is going to be set up and evaluate the integral of the area inside the circle and outside the cardioid. So that's going to be all of this. Okay, I am going to use the symmetry in this case. So I'm just going to do the top half here. And if I draw a cross section, I probably should have done this in the last one. So let's just say I pick a random thing here. The outside minus the inside. So that's what we're calculating. So I'm going to do 2 times the integral. For the top half, it's going to be from this theta, which is pi over 3, to this theta, which is pi. The outside is now 6, so we're going to have 1/2. 6 squared minus the inside is the cardioid. And again, we can just type this all in the calculator to get an answer. And there's our area. For the last one, we want to set up and evaluate the integral for the area that's inside both of them, which is everything that's left. So it's this area and this area, all of this. When we look at these cross sections, on this side, it is just the circle. For these ones, it's just the cardioid. So I'm just going to add the area of the circle for its part and the area of the cardioid. I'm going to, again, double. So I'm going to do the circle. So the circle area would be this to this, but I'm just going to go from 0 to pi over 3 of 1/2 the circle, which is 6 squared. And you could just do that as the area of a circle, but we can also use polar. So then this one is going to be from pi over 3 to pi of 1/2 the cardioid squared. So this here, and double it, plug that in the calculator and get 56.788. In the next problem, we're going to find the area enclosed by the inner loop of a Limason. So if I were to graph this, the amplitude is 2, the period is 2 pi, the vertical shift is 1. Okay, so we have a midline at 1, and then we're going 2 above that and 2 below that. Okay, so we're gonna graph. It's a positive cosine, so it starts up at the top, goes to the midline, to the minimum, to the midline, to the top. Okay, and if we were to graph this Limason, the inner loop comes from this part here. So you can graph it on your calculator to confirm that, but that's where the inner loop's going to come from. So I need to find those points. So that's going to be when 1 plus 2 cosine of theta is equal to 0. So where cosine theta equals -1/2, and that's going to occur. So we're looking for the x value to be -1/2, so that's 2 pi over 3 and 4 pi over 3. So my integral is going to be the integral from 2 pi over 3 to 4 pi over 3, 1/2, 1 plus 2 cosine theta squared d theta. Again, use our good old calculator and you'll get 0.544. Alright, next question, we're going to find the area common to circles 4 cosine theta and 4 sine theta. So for cosine theta, do that. For sine theta, going to be that there, a little wonky. So the area we want is this area in here. Okay, but this one's a little bit tricky. If you look at it, if I do my cross sections from the center out to the edge, the only thing we hit is, in this case, green one, which would be the cosine, or if I go from here to here, we hit the sine. So what we're going to do is we're going to split this, and you can either do the integral from 0 to pi over 4 of this one, or from pi over 4 to pi over 2 of the cosine one. Sorry. And if you picture the rectangular curves of cosine and sine, cosine's going to be here, sine's going to be here. So the full circle will be from 0 to pi over 2, but we just want half of that. So I'm going to double the integral. I'm going to go ahead and do the sine one, this one up here. So I'm going to go from 0 to the intersection point, which is going to be pi over 4, 1/2 for sine theta d theta. Okay, or you can do the other one from pi over 4 to pi over 2. So this is going to be 2.283, and if you pick incorrectly, it's going to give you a 0. Alright, find the area of the region inside the cardioid 2 plus 2 cosine theta, and to the right of r cosine theta equals 3 pi over 2, which is really the vertical line x equals 3 over 2. So I'll go ahead and draw this. Okay, so if I plug in cosine of 0 is going to be at 4, 2, -2. So there's the cardioid. And then we have the vertical line x equals 3/2. And we want the area to the right of it. Okay, so what I need to do is figure out these theta values. So I'm going to set 2 plus 2 cosine theta equal to, if I solve this for r is going to be 3 over 2 cosine theta and we're going to solve this equation. So I'll multiply this over. So we'll have 4 cosine theta plus 4 cosine squared theta equals 3. So 4 cosine squared theta plus 4 cosine theta minus 3 equals 0. Factoring never goes away. 2 cosine theta minus 1, and a 2 cosine theta plus 3, because we're looking for the two numbers that multiply to get a -3, which would be 1 and 3, and those are either going to be 1 and 4, and you can trial and error. So either cosine of theta equals 1/2, or cosine theta equals -3 over 2, which is never going to happen. Cosine equaling pi over 2, or cosine equaling 1/2 is going to be pi over 3 and negative pi over 3. I am again going to use the symmetry to simplify this. So rather than doing this whole thing from negative pi over 3 to pi over 3, which you could absolutely do, I'm just going to double the integral from 0 to pi over 3. And then it's going to be 1/2 the outside squared minus the inside squared. So it's going to be the cardioid squared minus the line squared, so it's going to be this solved for r, and calculator says 10.180. Okay, here is an AP problem. So we have the graphs of r equals 2, so it's going to be the circle, and 3 plus 2 cosine. The curves intersect at 2 pi over 3 and 4 pi over 3. Let r be the region inside the graph of r equals 2 and also inside the graph of 3 plus 2 cosine theta. Find the area of r. So this is going to be, we're going to split this up into two integrals. Okay, one for the area of the circle, which you can just do this area of a circle formula and then just do 2/3 of it, or we can use the polar. And then this part for the Limason. So for the circle, and I'm going to do my doubling thing, we're going to have 2 times the integral from 0 to 2 pi over 3, 1/2 r squared. Then we're going to add that to 2 times, I'll do this one, so that's going to be from 2 pi over 3 to pi of 1/2 3 plus 2 cosine theta squared. Calculator gives us 10.370 for that one. These last two are just review problems. So as we start going through the semester, we start adding on our ability to do more and more parts of these free response problems. So a particle is moving with a non-zero velocity along the polar curve given by r equals 3 plus 2 cosine theta. Has a position x of t, y of t, with theta equaling 0 when t equals 0. The particle moves so that dr dt is equal to dr d theta. Find the value of dr dt at theta equals pi over 3. So we have r equals 3 plus 2 cosine theta. So dr d theta is just -2 sine theta. Evaluate this at pi over 3. So we're trying to find dr dt at theta equals pi over 3, which we are told is equal to dr d theta when theta equals pi over 3. And you don't have to write all this, I'm just emphasizing. So this is going to be -2 sine pi over 3, which is root 3 over 2, gives us a -√3. So what does that mean for the motion of the particle? If dr dt is negative, it's moving in the direction, it's the distance, it's moving towards the origin. Because what this r is, where's origin? Is how far away it is from the origin. So if that distance is decreasing, then that means it's moving closer to the origin. For the particle described in part B, dy dt equals dy d theta. Find the value of dy dt at pi over 3. So we have to go back to good old y equals r sine theta. Remember, in polar, x always equals r cosine theta, y always equals r sine theta. So y equals, my r is 3 plus 2 cosine theta, sine of theta. So this would have been so you can just do this in your calculator if you want, or do the product rule and all that. Okay, so dy dt equals dy d theta at this. If you do the derivative of this in the calculator, you're going to get 0.5. So what does that tell me? If the y coordinate is increasing, if this is positive, that means the y coordinate is increasing. And that is how we do polar area.